right, in this video we're going to talk about finding limits. I have 4 different limits written down here from graphs, and you might notice I don't have a graph, so we're going to draw a graph. So we've talked about several different ways to think about finding limits. We've talked about using tables, we've already talked about using graphs, we've talked about using function equations, so all of those ways are valid and all of those ways might be useful in this problem, but I want to focus a little bit on graphs, and in particular just a little refresher about how to graph a function like this. So this is a piecewise defined function where we have the function given by different pieces of equations for different pieces of the domain. So piecewise defined function, hopefully you remember from algebra. All right, so I'm going to start by graphing this function, and this works especially well when you can easily get a good graph. And so you could use technology to help, but they often have trouble with piecewise defined functions and showing clearly what's happening at those breakpoints where it switches x less than 0 for the first part, and then x greater than or equal to 0. So it switches at x equals 0, and it switches here at x equals 2, which you might notice is exactly where we're interested in for the limits here. So technology often would have a difficult time graphing a function like this correctly, but fortunately this one's pretty easy to just graph on your own. You might notice that the pieces are all very simple functions that you know a lot about what those graphs look like. These first two are pieces of parabolas, x squared minus 1. You can think about that as just a basic y equals x squared parabola shifted down 1 unit. F of x equals x squared, that's just a basic y equals x squared parabola. And then a straight line, y equals 3x minus 2. So these are all pretty easy to graph. If the equations were more complicated, I maybe wouldn't use a graph to do this, but because these are all pretty easy and I can think about what the graph looks like pretty easily, that's one way that can help me with these limits. All right, so first of all, I need an xy coordinate system. And so I'm just going to graph each piece, and I'm going to do these in different colors. You don't necessarily need to do that, but just to kind of help us focus on the different pieces here and what's happening. All right, so this first piece, we have y equals x squared minus 1. So that's your basic y equals x squared parabola, but shifted down 1 unit. But we only want the part of that where x is less than 0. So just left of x equals 0. So if you just think about that basic parabola, y equals x squared, and then shifted down 1 unit, the vertex would be down here at -1. But I only want to graph the part of that parabola that is left of x equals 0. So it says x less than 0, so we're going to be left of x equals 0. All right, so I'm going to have an open circle where the vertex of that parabola would be, because x equals 0 is not included there. And then I'm just going to draw the left half of that parabola. And so you might think a little bit about where that would cross the x-axis here at x equals -1. So just thinking about kind of basic parabola shifted down 1 unit. All right, so that's this part, y equals x squared minus 1 for x less than 0. And I can write that here if I want. I'm not going to, just I don't want to clutter up the graph too much here. All right, and then the next part is y equals x squared. So that's basic parabola with vertex at the origin. But I only want the piece of that parabola that's between x equals 0 and x equals 2. And notice that I am going to include x equals 0, but on this side I'm going to go right up to, but not include x equals 2. So if you just think about that basic parabola before I shifted it down 1, like I did for the other one, basic parabola with vertex at the origin. So the origin would be where we have x equals 0, so I'm going to put a filled in point there. This is on the parabola y equals x squared. And then I'm going to go over to x equals 2. So I might think a little bit about where that parabola is going to be at x equals 2. So if I had the whole parabola, that would be at 4. 2 squared is 4. So when x is equal to 2, the y coordinate would be 4. But I'm not going to go all the way to that y coordinate of y equals 4 because remember x equals 2 is not actually included. So I'm going to put an open circle. And I'm going to go ahead and label where that open circle is at, 2, 4 there. And then we've got the part of the parabola. Just not a perfect drawing of that, but an okay sketch of that parabola. So open circle at x equals 2 because it's not included in that part. Filled in point at x equals 0 because that is included in that part of the parabola. All right, and then I have one other part of the parabola, y equals 3x minus 2, and I just want the part of that when x is greater than or equal to 2. So you might think about that as the line y equals 3x minus 2, which has a y-intercept of -2 and a slope of 3. And so a lot of times students use a y-intercept and a slope to think about how to graph a line, and that's a perfectly good way to do it. The only difficulty with that here is that the y-intercept is where x equals 0, and that's not really the part of this line that I want to show. I don't really need to show the part of the line where x is equal to 0. So you could use that y-intercept and slope to graph the line and then just erase the part of it where x is less than 2. I only want the part of this line where x is greater than or equal to 2. Or you could also just think about, to graph a straight line, really you just need any point on the line and then slope to think about that. So I'm going to just figure out where the point is at when x is equal to 2 on this line. So I'm going to put in x equals 2, and I'll have 3 times 2 minus 2, so 6 minus 2 is 4. So this line will actually go through the point at 2, 4. So I had an open circle there from the part of the parabola, y equals x squared, but the line actually meets right there. So that I have an actual point there at 2, 4 because that's on this part of the line. And notice the other two parts don't meet up, but these two parts here do happen to meet up at x equals 2. All right, so there's one point, and then I could just plot another point. I could put in another number, say x equals 3 or something like that. Or I'm going to just count out rise and run and think about the slope. So from that point at 2, 4, I'm going to use a slope of 3. So that's rise 3 and run 1. So from this point at 2, 4, I'm going to go up 3 and over 1 to get another point on that line. So that will be at 3, 7, and then the line just going to continue on up with that same slope. So I have a parabola and a line, part of a line, that happen to meet right there at x equals 2. All right, and then I have some limits here to think about. So that's really what we were trying to do here, is figure out these limits, but we're just going to use this graph to help us do that. All right, so this first one asks us about the limit as x approaches 0 of f of x. So that's asking us about when we are on the graph of the function near x equals 0, but not at x equals 0, and we go toward x equals 0, what happens? So I'm just going to think a little bit on each side of x equals 0 and think about, as I go toward x equals 0, what happens? And one thing that you might notice is that we go to different places. All right, so a way to write that is to say that as x approaches 0 from the positive side, so that would be the right side of x equals 0, the limit as x approaches 0 from the right, from the positive side of f of x. So I'm thinking about on the positive side of x equals 0. So over here, when I'm close to x equals 0 and go towards x equals 0, the function values go toward 0. So this limit is 0. And as x approaches 0 from the left, from the negative side, so a little bit less than x equals 0, the limit of this function, so when I'm a little bit left of x equals 0 and then I go toward x equals 0, those y values are going toward -1. And since these do not agree, then our overall limit does not exist. And I'm going to abbreviate that here. DNE does not exist. Our homework does that a lot too. Abbreviate DNE for does not exist. So these two have to be the same. These two one-sided limits have to be the same in order for us to have an answer here for our overall limit. Remember, there are really 4 answers you could ever have for a limit question. One of them is a number. We got that for one of these one-sided limits here. So a number. You could have infinity or negative infinity, or you could have does not exist. Only 4 possible answers: number, infinity, negative infinity, or does not exist. All right, so this one does not exist because the two one-sided limits are different. All right, this next one asks us what happens to the function output values as x is getting close to 2. So I want to look at my graph on both sides of x equals 2 and think about going toward x equals 2 and think about what happens with the function values. And on this one, they both go to the same value on both sides. Remember, I didn't really have a point on the parabola, the pink function there. I do have a point on the line, the green part of the graph here. But really, a limit, remember, is not really asking you about what happens at that point. It's asking you about what happens as you get infinitely close to that point. So even if I still had an open circle there, if these are both headed toward the same place, I would say that this limit is 4. Okay, so a number for that limit. And I could explain why by explaining, like I did here, that when I approach 2 from the right side, so a little bit bigger than x equals 2, the y values approach 4. And when I approach 2 from the left side of 2, so just slightly less than 2, the function values also approach 4. And because these do agree and are both 4, then that's why we have this overall limit. So you don't necessarily need to write this kind of stuff out, but if you wanted to explain to someone why the limit was 4, sometimes in the online homework it'll ask you for these one-sided limits and the overall limit as well. So just paying careful attention to whatever it's asking you to do. All right, these next two are asking us about what happens to the function output values, so y coordinates, when x approaches infinity or negative infinity. And so we talked in class a little bit about why that's kind of a weird thing to say x approaches infinity, because it can't really get close to infinity. But what we're saying here is that when x grows without bound, so when x gets bigger and bigger and bigger in the positive direction. So x grows and grows and grows in the positive direction as far as it can go, is what this is saying. And it's asking us what is happening to the output values of the function. So I'm going to look on the graph of my function, and I want to think about as x grows, so I want to be on the graph of the curve, not necessarily down here, but I want to go to the right, which is the direction of the positive x-axis. So I want to think about what's happening to the output values of the function. And you can see here, those output values of the function are just getting bigger and bigger and bigger in the positive direction. So when x grows in the positive direction and just keeps growing and growing and growing without bound, the same thing happens to the y values here. So the y values approach positive infinity. Okay, so let's look at this last one here. This is asking us what happens when x grows in size but goes in the negative direction. So x grows in size. Have to be a little careful about wording there because negative numbers are smaller than positive numbers. But x grows in size but to the left or in the negative direction. Okay, so when we think about the graph, when I go as far as I can go on the graph to the left, what is happening to the y values of the function? All right, and so here, as x goes to the left, you can see that those y values are going higher and higher and higher. And so on this one, the y values are approaching positive infinity on both sides. The y values are just going up on both kind of ends of the graph there. All right, so again, remember, 4 kinds of answers that you can possibly ever have on any limit question. A number, does not exist, or positive infinity, or I didn't have an example here where the answer was negative infinity, but that would be when the y values are growing in size, but in the negative direction. So only 4 possible answers. All right, we'll look at some other examples where we look at other methods for finding limits.